Alright guys, welcome back to another video of chapter 4 curve sketching. My name is Steven and today we'll be learning more about concavity and points of inflection. Okay, so what exactly is point of inflection? Point of inflection basically means, say we have a graph. Okay, we have a graph as in something like a cubic expression. We have something like this. So in this graph, in this cubic expression, point of inflection basically means, okay, we have these two curves. You can basically break down this cubic function or cubic graph into two different curves. This curve, and then another curve is this curve. Okay, this curve. Alright, so from this, that you can pretty much see that this curve is facing down this way. And then the other curve of the graph, it's facing upwards. So something like this. Okay, so point of inflection basically means the point in the middle where the graph started changing its concavity from like a cup facing downwards to upwards. So basically that means that, okay, at which point of the graph that the concavity started changing from facing down to facing up? And if we analyze this, it's somewhere in the middle here that started changing its concavity from downwards to upwards. So point of inflection basically being this. And if I have to give another example, say for example like say we have a function like this, a quintic function like this, and if we break this down, we have this curve that is facing upwards, and then we got another curve. We got another curve that is facing downwards. And then after that, we have another curve that is facing upwards. So from this, points of inflection basically means, okay, the middle point, the middle coordinates where the graph started changing its concavity from facing upwards to downwards. Same goes with the point of inflection here as well. The coordinates where the graph started facing down, the graph started changing its concavity from facing downwards to upwards, from this to this. So in this graph, we have 2 points of inflection, and points of inflection basically mean this. Alright, so how do we find point of inflection, right? So the way that we find point of inflection is quite simple. In the previous videos, we've learned that if we have a function f of x, if you want to find a critical point, we generally find the first derivative of f of x and equal to 0. That's how we find a critical point. Keep in mind though, this is only one of the strategies that we can use to find a critical point. There's another way mentioned in the other video that you can check it out later on. And basically, point of inflection, how do we find it? The way that we find it is we just find the second derivative of f of x and then equal to 0. And then we will get x equals yada yada. And then if we substitute, okay, wait, I think a will be clearer to understand. A into yada yada, which is x value. And then if we substitute a in place of x, we will have another y value, which will result in a comma, oh wait, no. Okay, say we have a function f of x, and from the previous videos that we have learned that in order for us to find a critical point, we have to find the first derivative of this function and then equal to 0. Generally, the general way of finding a critical point is to find the first derivative of f of x and equal it with 0. But keep in mind that this is not the only way to find a critical point. There is actually another way, which was mentioned in the other video. You can go check it out later on if you want. And then how to find point of inflection? Basically, you find the second derivative of f of x and equal it to 0. And then you get an x value, which in this case I will consider it as a. And then we substitute this a into the original function, then we'll get the y value, so that we will have a point of inflection at a comma f of a. Okay, so in a nutshell, we can find a point of inflection by finding the second derivative of a function and equal it with 0. Okay, so from the previous slide, we have learned that in order for us to find an inflection point, we have to find the second derivative of the function and then equal it with 0. Right. So then, it's not always the case that we will find an inflection point if we find x using the second derivative and equal it with 0, because inflection point, in order for an inflection point to exist, okay, in order for us for an inflection point to exist, it has to change sign. It has to change sign in f of x before and after the point. And from this, what I mean is we cannot straightforwardly conclude that if we find the second derivative of f of x and equal to 0, we will always get an inflection point. That's not always the case. So in order for us to actually determine if it's an inflection point or not, we have to see the surrounding f double prime of x value before and after the point, which means that, okay, we have found a potential x value for inflection point. Okay, what is the nature of f double prime x before and after the x value? Does the sign change? Does the sign change the same? Does the sign remain the same, or did the sign change? Based on that, we have to determine if it's an inflection point or not. So inflection point basically means if the sign changes before and after the x value, that is an inflection point. Okay, so we can also find using, like, once we have found the inflection point using the concavity and the concavity that I mentioned earlier slide, another thing that we can add on is we can also try to find critical points using the second derivative. I mentioned about this in the earlier videos that there are actually two ways to find to classify the nature of critical points. Let's say like maximum, minimum, or horizontal tangent, vertical tangent, cusp, or sharp corner. Like, there are two ways to find it. The first way is to draw a table using test values and using test values before and after that number, after that critical number. That's the first way. And the second way is to classify the critical point using second derivative test. Okay, so we have a critical point, which we got it from finding the first derivative of x equal to 0. Okay, and then we have to find, and then we find the second derivative of f of x, and we substitute the x value that we got from here, the critical number. If we substitute the critical number into the second derivative of it, and if we get like greater than 0, which means it is concave up. That means in terms of graph, we'll have something like this, and we'll get a minimum point. Okay, so if we find the critical point using f of x equal to 0 plus, we find f double prime of x and then substitute the critical number, and if we get less than 0, we will have concave down. Concave down, which will be something like this, so it will be a maximum. Alright, So if we have a critical point equal to 0 plus we find the second derivative of f of x and then we get equal to 0, it means that no conclusion can be made. It needs more work. Why? Because if the second derivative of x using the critical number that we got from the first derivative still equals to 0, it can be an inflection point. Oh my God. Nor maximum nor minimum. Okay, what do I mean by this? Let's prove that by doing some example questions. So let me delete this. So the first question is, find the following function, find the critical points and classify them using a second derivative test. So just as always, find the first derivative of f of x equals 3x squared minus 6x. And because it's a polynomial and we want to find the critical point, we'll equal f of x equal to 0. We can factor off 3x from here, so x minus 2 equal to 0, which will result in x equal to 0 and x equal to 2 being critical numbers. Alright, so then we will verify it by substituting the original function. So f of 0 equals to 2 and f of 2 equals 8 minus 12 plus 2, which will result in negative 2. This means that f of a has been defined. So we have verified and meet the first criteria of finding a critical point. So the critical points are 0, 2 and 2, negative 2. Okay, we have found the critical points. Now we have to classify whether if it's a maximum, minimum, or maximum, minimum, maximum or minimum. So we will find the second derivative of f of x, 6x minus 6, and we'll include the critical numbers into the second derivative of f of x. So if we substitute 0, we'll get negative 6, and if we substitute negative 2, we will get negative 12. Oh no, we have to substitute 2. If we substitute 2 into it, we will get 6, which is a positive number. So that means when we substitute 0 into the second derivative of f of x, we have negative 6, which means that it is less than 0. Because it's less than 0, the graph should be something like this, and then it will be a maximum point. And this is because greater than 0, the graph should be something like this, and it is a minimum point. Alright, so to conclude, 0, 2 is maximum point, and 2, negative 2 is minimum point. That's it. Alright, let's move on to the next question. So the next question is, we have to find the critical points and classify the second derivative test just like before. So we find the first derivative, which is 4x cubed. Right? So if we equal the first derivative of f of x with 0, we get 0. Okay? And if we, from then on, we will get a critical number being x equal to 0, and we substitute x equal to 0 in the original function, which will result in 0 as well. So 0, well, this is verified. verified criteria. Alright, since we had a definite y value answer, this is considered 0, 0 can be considered as a critical point. Alright, we found a critical point, and now we have to classify whether if it's a maximum or minimum. So in order to do that, we find the second derivative, which will be 12x squared, and then we substitute x equal to 0 into the second derivative of f of x. And if we substitute 0 into it, we will get 0 as well. So come to think of it, okay? F prime of x equal to 0, and we substitute the x value we got from here in the second derivative of f of x, and you still get 0. And if you remember correctly, with the previous slide, I told you that if both the first and second derivative of f of x equal to 0, we can't conclude whether if it's a maximum or minimum. Alright, if that's the case, now that we can't find whether if it's actually a maximum or minimum, what do we do next? How do we approach it so that we'll know if it's either a maximum or minimum? In order to do that, we have to look at the function again. Function is f of x equal to x with the power of 4, which means it is a quartic function. It is a quartic function, so it would look something like this. Okay, so when you look at this, there is no exact point of inflection. Point of inflection, you usually finding like the second derivative of the function and then you equal it with 0. And that's not really the case here. There's no inflection point here. Okay, so it's either maximum or minimum. So because we understand and we know how the graph generally should look like for x power 4, we can conclude from here that it will have a minimum point. So 0, 0 is a minimum point. From this, what I want you to know is if we find both first and second derivative of a function and the both is equal to 0, we cannot conclude whether if it's actually maximum or minimum, and we need more work. We need more analysis for us to actually determine if it's a maximum or minimum. In this case, because it's x power 4, it's a quartic function with a leading coefficient being positive, so it is concaving upwards with no point of inflection. So this point 0, 0 must be a minimum point. I hope this explains the three statements that we have come up with earlier in the previous two slides with how to classify the critical points using the second derivative test. Alright, let's move on to the next question. So the next question is, for the following function, find the points of inflection in the intervals of concavity. Alright, let's find the intervals of, finds the point of inflection. First of all, we find the second derivative. So the first derivative is 4x cubed minus 12x. And then the second derivative will be 12x squared minus 12. Alright? And then we equal the second derivative with 0. So f double prime x equal to 0. We can factor off 12, so x squared minus 1 equal to 0, which we will get x equals to, oh no wait, let me not skip the steps. X squared minus 1 equal to 0, x squared equal to 1, and then we will get points of inflection plus or minus 1. Okay, so this is the x value of points of inflection. And if you want to find the y value as well, you can substitute it into the original function and you will get both coordinates of the point of inflection. But yeah, I'll do it right now. So f of 1 equals to minus 6 minus 5 negative 10. And then if we substitute negative 1 minus 6 minus 5, we got negative 10 as well. Alright, so the point of inflection is -1, -10. Alright, so the points of inflections are already, we've already searched the solution for the points of inflection. Now what we have to do is we have to find the intervals of concavity. Okay, remember the previous videos where we find whether a function is increasing or decreasing before and after the critical points? Like, you remember that one way that we have to find tables and then we have to determine if it's increasing before that critical point or decreasing before that critical point? Basically, the way that we find interval of concavity is similar to that as well, except we have to make use of the second derivative. Alright, so let's draw a table x equals -1, which we write it as like a point of inflection, and then x equal to 1. Then we will use the domain, which basically means that, okay, before the point of inflection x equals -1, we have on the left side we have -infinity to -1, and then the actual point, which is x equals -1, and afterwards we will have from -1 to +1, and then point of inflection being a +1, and then after that on the right side we'll have 1 to infinity. Okay, and then the second derivative of f of x, and then the first derivative of x. So when we were finding this, we found out that there is zero, because these are point of inflection, and when we substitute -1 into the second derivative of x, we'll get 0, as we calculate here. Okay, so afterwards we will find basically f double prime of which is less than -1 is -2, and if we include -2 into it, we'll get 36, which is a positive number. And then afterwards we will put in f of double prime 0, and then what we will get is a negative number, that being -12, because we included 0 in here. So 12 into 0 becomes 0, so we're left with -12. And then afterwards, I will try putting in x value of 2. If we put in x value of 2, 12, 36, we got 36, which is a positive number. Okay, these are points of inflection, as we have calculated here already. So inflection, and then the same goes with this one as well, point of inflection. Alright, in order for us to have a point of inflection, I mentioned earlier that, okay, before these two coordinates, before and after these two coordinates, there must be a sign change. And according to this, we do have sign change as well. At first we were having a positive, and then we have a point of inflection. Afterwards we have negative, another point of inflection, and then we have positive again. Basically what it means is that we will have a concave up here, like this, and then we'll have a point of inflection, and then we'll have concave down here, and then because it becomes positive again, we'll have concave up here again. Alright, so from this we can conclude that intervals of upward concavity includes -infinity, -1, union 1, infinity, and then downward concavity is -1 to +1. So if you look carefully at this, it's kind of similar to the way that we find the intervals of increasing and decreasing. At first we will find the critical point, and then we'll find the values before and after those critical points and see if there's any changes, and then from them we will determine which part of the domain are the intervals of increasing, and then which of the intervals are decreasing. Same with this as well. We find the values before and after those point of inflection, see if there's any sign changes, and there is, and therefore it becomes the point of inflection, and then we can determine the upward concavity intervals and downward concavity intervals. Wait, what are some key takeaways from this lesson? Alright, so first of all, you need to know how to classify critical points using second derivative test. remember with the three scenarios that we have, from x equal to 0, and then from x f double prime of x greater than 0, and then same goes, but then f prime of x less than 0, and then same goes, but f prime of x equals to 0. These three scenarios. So you must know how to classify it using the second derivative test, and then the second thing is we need to know how to find intervals of concavity. Remember, we try to find the point of inflection. We find point of inflection, we put it in a table and see if there's sign changes. And that's a way to find intervals of concavity. And then apart from that, we will have some communications or knowledge questions that we can possibly ask, which is if x equal to a is inflection point, then f double prime of a equal to 0. This is correct. If a point, if an x value is an inflection point, then if we find the second derivative of a function and then substitute that x value, we'll get 0. We'll definitely get 0. This statement is correct, but then if it's the other way around, say if second derivative of a equal to 0, then x equal to a is inflection point. This is not correct, because this is not always the case. Why? It kind of ties back to the one that we mentioned here. Because if we find the second derivative of x and it still equals to 0, you can still see that we can't conclude anything. We can't exactly say if it's actually an inflection point, maximum or minimum. Therefore, this statement is not always the case. Therefore, it's not true. All right. And then sometimes, when we write concavity intervals, vertical asymptotes can come into play. So we gotta beware of vertical asymptotes. Because, say for example, with the rational functions, right? Say rational functions would be if it's something like this, these are vertical asymptotes. Alright? So this is concave up. And then this part is concave down, then this part is concave up. And if we were trying to write the concavity intervals to rational functions, we can't just write from here like negative infinity to like positive infinity, because in the middle we have an interval where we have concave down as well. So what we have to do is negative infinity to the value of the vertical asymptote, okay, and then the intervals between two different vertical asymptotes, which will be the concave down intervals, and then lastly we'll have a vertical asymptote to positive infinity, which is and concave intervals as well. So inflection point does not necessarily have to exist for us to have a concavity. Take a look at these kind of rational functions. We don't really have an inflection point. We can't really pinpoint where the graph actually changed its concavity from facing upwards or downwards. But still, concavity still exists without the need of inflection point. So when we write concavity intervals, we have to be careful with it. And that's pretty much it for this lesson.